Hi, my name is Kayla Hookham. Today I'm going to talk about the skip list. First, what is skip list? Skip list is a probabilistic alternative to balance tree, which is balanced by consulting a random number generator. Skip list allows efficient and faster operation on search, insertion, and deletion of elements in a sorted list. Skip list is organized in layers, which each layer having a smaller number of elements than the one below it, and the bottom one being the original regular list, and the higher one being the skipping layers, which allows faster navigation between nodes that's far apart. We have other data structure like linked lists, arrays, and trees, and hash tables, but what is the reason we need skip lists? The reason we need a skip list is it allows better performance and efficient search and insertion and deletion than other data structures, and it is very simple to implement and it uses less space compared to balance trees, making them easier to work with, and it can handle large data sets efficiently. I'll show a comparison between different data structures later in the PowerPoint. Okay, William Puh is the developer of skiplist, which he invented in 1989. The reason he developed this skiplist was he wanted to invent something that offers a simple but also efficient alternative to balance trees like AVL or red and black trees by leveraging randomness to maintain multi-level linked lists that skip root elements for faster traversal. Some of the real-world application for skip lists is in memory database, file system, peer-to-peer system, cache system, and sorted data storage. And let's talk about the structure and components of the skip list. So first let's talk about linked lists. If we search in linked list, for example, if we do search 6, we're gonna go 1, 2, 3, 4, 5, and 6, and we found it. And if we search in a normal sorted linked list, we'll have a complexity of O(n). How can we improve this? And the way we could improve this is by using skip list. Some of the components in skip list is we have a node which stores each values and which also has a forward pointer. It has a level, which is a hierarchy. We have the level, which we have from the bottom layers to the maximum level, which is the top, which bottom one is the original one, and each layer above it has less nodes than the level below it. Probability factor P is the probability that a node will also appear in the next level, and the common set of number that we use for the probability factor is 0.5, 50%. And we also have head and tail, which marks the start and the end of each list in all levels. And let's talk about probability factor. Probability factor P is a chance that each node will also occupy the next level. The way we figure out if the node is also going to occupy the next level is by using the coin flip technique. The coin flip technique is used to randomly decide how many levels the node will occupy in the skip list. If you visualize it, it's like flip a coin, and if it's heads, it's going to occupy the next level. If it's tails, it's not. And P is commonly set as 0.5, and higher P means there's going to be more nodes in higher level compared to when there's a lower P. And if there's a higher P, it means that we will have faster search time, but because we're going to have more nodes in the higher levels, it means that we're going to use more memories. When we have a lower P, we'll have the opposite, where we'll have a lower search time, but we'll have less memory use. By looking at the graph on the right side, it shows how the probability factor of P, the amount of nodes we have, how that's going to influence the operation and the time it takes. In skip list, there are some key properties and invariants that must be maintained. First, we need to have sorted orders. Skip list only works in sorted levels, and every level needs to be sorted to maintain efficient operation like search, insertion, and deletion. The second thing we need to have is head node, and head nodes will point to the first node in each level. And the third thing we need to have is a single pointer. Each node needs to have a single pointer to the next node, so we could navigate from one node to the next one. And skip list, we can't have like an arrow behind the current node. And next, we have the levels. And levels are essential to skip list, which allows fast operation with search, insertion, and deletion. And starting from the bottom level, the original list is considered as level 0, and each level on top is level 1, level 2, and level 3. And then each level has nodes that's randomly selected by using the coin flip technique that I talked earlier. Okay, next let's talk about operation like search, insert, and deletion. First, let's talk about search operation. How the search operation will work is we're going to traverse the layers from top to bottom, skip through the nodes until the next node is greater than the node we're searching for. And if the next node is greater, we're going to go to the layer below it until we find the desired element. And the average time complexity for the search operation is O log n, where n is the number of elements in the bottom layers. And to have a better visualization of how the search operation works, I'll show you a step-by-step visualization how the search operation works. In here, we have two layers. The bottom level, which we call normal lane, is the original linked list element. And then anything above the normal lane is called express lane, which is the upper level which connects some of the subset of elements from the normal lane. Okay, let's do search 6, like how we did in the linked list, starting from the head, which connects to the very first node in the list. The very first one is 1. We're going to see if the next node is greater than, equal to, or less than the one that we're searching for, which is 6. Since 3 is less than 6, we're going to go to the next node. We're going to do the same thing, compare the 5 to 6. Since 5 is less than 6, we're going to go to the next node. We're going to compare 7. And since 7 is greater than 6, we're going to go to the bottom level. We're going to go down here and then go to the right. 6. And we found it. And then if we have more layers, for example, if we have, since the previous one only had one express lane and one normal lane, this time we have two express lane. More layers of express lane allows faster search time. We're going to start from the 1. We're going to compare if 5 is less than, greater than, equal to 6. And since 5 is less than 6, we're going to go to the next node. And next we're going to do the same thing. We're going to do a comparison with 9. And since 9 is greater than 6, we're going to go down. We're going to go down. And we're going to compare with 7. And since 7 is greater than 6, we're going to go down again. And then we're going to compare with 6 over here. And since 6 is the same thing as what we're searching for, we find it. If we have more express lane, which it allows faster implementation. And this is how the search operation has the average time complexity of O log n. Okay, next we're going to talk about the insertion operation. Insertion operation, first we're going to, since we have different layers in the skip list, we're going to determine how many layers the elements we're going to insert is going to occupy. And this is found by the coin flip technique. And we're going to find where the node inserting is going to fit into the list. And then even after the insertion happens, the list needs to maintain a sorted order. And then the average time complexity of insertion is going to be O log n. And next, let's do a step-by-step visualization of how the insertion works. For example, if we do insert 12, we're going to find where the 12 is going to fit into. We're going to do the same operation that we did in search, and we're going to traverse until we find where it's going to fit. And over here, when we reach 11, since the next node is 13, which is greater than 12, and the current node 11 is less than 12, we know that it fits between them. And then when inserting, as I described earlier, it's gonna use the coin flip technique to find how many layers that node is gonna occupy. First, it's gonna be height 0, and we're gonna use the coin flip technique to see how many layers it's gonna occupy. For example, if the height was 0, it's only gonna insert in the normal lane, but if the height was 1, it's gonna be inserted in both the normal lane and level 1. If the height is 2, it's gonna have another layer on top with just the 12. And then as the height increases, we're going to create new level, and then we're going to insert the current node 12. And this is how the insertion operation works, and at the end it'll have the average complexity of O log n. Next, let's talk about deletion. First, we're going to find the elements we're going to delete, like how we did in search, and then remove that target node and delete it from all layers. Third, we do the deletion operation. It needs to maintain a sorted order, and at the end, the average time complexity of deletion in the skip list is gonna be O log n. Let's do a step-by-step visualization of how it's gonna work. First, we're gonna find the target node 11, which is over here. When we find it, we're gonna delete it. But for example, if the target element is occupying more than one layer, it's gonna delete both of them. The pointer is gonna point to the next node. And that is how the deletion operation works. And as similar to search and insertion, it will have the average complexity of O log n. Okay, let's do a complexity analysis. So in a skip list, instead of like linked lists when we traverse one node at a time, the skip list allows skipping across multiple nodes, which reduce the average time complexity compared to the linked list. And Because of that operation, search, insert, and delete, it has a average time complexity of O log n, but at the same time it's gonna have a O(n) in the worst case. And then the space complexity of skip list is going to be O(n). This is a comparison that William Puh, the developer, showed us in one of his articles, which has a comparison between different data structure and how each search time, insertion time, and deletion time is compared to skip list. And as you could tell in the graph, skip list performs competitively, especially in insertion time and deletion time. For search operation, skip list is significantly slower than non-recursive ABL tree, as you can tell over here. Next, we're going to talk about why in skip list we have an average complexity of O log n. And in skip list, each node is prompted to the next level with probability p, and we use the coin flip technique to see if each node is gonna occupy the next node. In skip list, the geometric distribution is commonly used because it allows a good balance between search speed and insertion and deletion efficiently, which offers an average time complexity of O log. And let's talk about the pros and cons of skip list. Okay, first let's talk about the advantage. The advantage of skip list is that skip list is very solid and trustworthy, and inserting a new node is extremely quick. And it is also easy to implement compared to like hash tables and binary trees, and even though it has a worst case of O(n), as the number of nodes in a skip list increases, the possibility to reach the worst case is gonna decrease. And skip list also requires only O log n time in the average time for all operation, and finding a node in the list is very straightforward. And the time that we should use skip list is when we want a fast access using the sorted data, since skip list only works in the sorted data, and when you want an easy implementation alternative, and when we want a average case operation of O log n over worst case guarantee of O(n). Next, we're going to talk about the disadvantage of skip list. Some of the disadvantage is, since skip list has multiple layers, it does need a great amount of memory. In a skip list, it's a single pointer where each node is pointing only to the next node. It doesn't allow reverse search. And the worst case complexity of the operation, like search, insert, and deletion, is O(n), and then skip lists are not cache friendly because they don't optimize locality of reference. So there are some times that we need to avoid skip lists. When the memory space is limited, when you're not using a single pointer, and if you want to go back and stuff, if you want like a double pointer, skip list might not be the best choice. And when you want a better worst case than O(n), since other data structures does have a better worst case than O(n), so if we want something better than O(n), we might want to avoid using skip list. Next, let's talk about some implementation and consideration and some potential pitfalls. First, implementation consideration is skip list use geometric distribution with a tunable probability of p, and we need to create a max level cap, or else there is a possibility that the levels could be very huge, which causes to take more memory space. And we need to create a head node for each level, and at the end we need to have a forward pointer pointing to a null pointer. And then some of the pitfalls of skip list is, since the node levels are random, the levels can have a skewed level distribution, which means that a level can have nodes from the very beginning, but the end could be very empty, which causes an inefficient operations. And as I talked earlier, having no max level capacity can create a way too high level, causing inefficiency in the use of memory. Some of the trade-offs of skip list compared to alternative data structures is that skip list has a average complexity of O log n, but has a worst time complexity of O(n). And while others like ABL or red and black trees have a worst case of O log n. So in this case, if the worst case complexity is very important to you, you might want to use like other data structures like ABL and red and black trees, which has better worst case complexity. Skip list can use more memory space compared to ABL tree, red and black trees, and hash tables because it has levels that takes more memory space. While I was like searching and learning about skip list, there were some interesting things that I learned. There were two things that I thought was very interesting, and the first thing that was interesting was to learn that the node for each level is chosen randomly using the probability p. The second thing was I thought it was nice that after each operation, it's gonna maintain a balance, which these are the two things that I thought was interesting. And this is the citation page of the sources that I used to learn about skip list. Thank you so much for listening.